Hello, today we're going to discuss some different properties of waves, including resonance, standing waves, and beats. Resonance is a situation where an object has something called a natural frequency or what's called a resonant frequency. All objects have it. So when you hit a drum or pluck a string or hit a tuning fork, the frequency that's created, that is the object's resonant frequency. Okay? It depends on the shape and size of the object, the elasticity of the material involved. All those different factors play a role in the object's resonant frequency. When you apply a frequency that is at the object's resonant frequency, you get something called resonance. And resonance is an increase in the amplitude of the vibrations that are occurring. Okay? A place where you've seen this is when you're on a swing set. Okay? When you pump your legs or when you lean back and lean forward. In order to go higher and higher, you do that at the frequency that you're traveling. So you're applying a frequency at the frequency that you're already going back and forth at, which causes the amplitude to increase. Another place you see that is the old breaking the glass with the singer, the opera singer. The glass has a natural frequency. If the opera singer sings at a frequency that is the same as that natural frequency, it's going to cause the particles in the glass to vibrate more and more and more, which then causes it to eventually shatter because it is vibrating so much. Standing waves are created in these different objects based on the resonant frequency. It's based on the type of the object and the length of the object. Standing waves occur because of interference of two different waves that are moving in opposite directions. One wave is called the incident wave. And let's say that it starts here and goes to the wall. Then it reflects back, and so we have the reflected wave, which moves the other way. So we have these two waves that are moving in opposite directions. They have the same wavelength, they have the same frequency, and from that we get this standing wave pattern. It kind of looks like when you look at a ceiling fan, it all kind of looks very like it's just one disc moving around because it's going so fast. That's what these areas look like here. These are called the antinodes. Okay? Antinodes occur at places of maximum vibration. Okay? So maximum vibration for the antinodes. The place where no vibration occurs are called the nodes. Okay? So there's no vibration at the nodes. Okay, so on our diagram here we have 4 nodes and we have 3 antinodes. Our nodes are located here, 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 and here. And my antinodes are located, as it shows here, 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 and here. Okay? So 4 nodes, 3 antinodes on that diagram. We have 3 different places we're going to find standing waves. The first one we're going to look at is a standing wave on a string. So let's say we have a string that is length L. Let's say somebody is holding this end down here and causing it to vibrate back and forth. And let's say the green point over here is a point on the wall. So the wave will travel into the wall, the incident wave, and then it will get reflected back this way. So my incident wave is green, my reflected wave is red. Okay? The length of the string is L. These numbers out here to the side we call harmonic numbers. Okay? Harmonics. The lowest harmonic, which is the highest wavelength but the lowest frequency, is called the fundamental frequency. Okay? So this one over here is the fundamental frequency. Like I said, it is the longest wave that can be formed on an object in terms of a standing wave, and it has the lowest frequency. Okay? All of these other frequencies, standing waves that can be formed, they're all multiples of that number. Okay? Those are the harmonic numbers. So our first wave here, so in order to determine what the wavelength is of this wave, we have to look at the length of the string and how many waves are on here. So this string is length L, right? How much of a wave is on this string L? Well, we know that a wave, when we think about what a wave looks like, waves look like this, right? Okay? So looking at this diagram over here, there's only half of a wave on here. So we would need a whole nother length L to create a full wave, right? So the wavelength of this first wave is going to be twice the length of the string because we would need another L in order to make a full wave. Okay? If we look at our next one, the second harmonic. Here we have one full wave. Okay? See, there's one full wave right there. So the wavelength of this one is going to be just L. Okay? The last wave we look at, the third harmonic, we have the incident wave here. We have the reflected wave coming back off of that. Okay? So to determine the wavelength of this wave, we have to look at basically how long is one wave. That's what we're looking at here. That is the wavelength. How long is one wave? So if we look at our wave down here, we see that we have 1.5 waves. Okay? One wave goes from here to here. There's one complete wave. And that one wave is 2/3 the length of the total string. So the wavelength here is going to be 2/3 L, or 2L over 3. Okay? As you can see, there's a little bit of a pattern here. If we went a little bit further in, you could probably see the pattern a little bit more clearly. But the general pattern for the wavelength of a standing wave on a string is that the wavelength is equal to 2L divided by N, where N is, again, the harmonic number. Okay? So the wavelength of a standing wave on a string, all the wavelengths that can be formed follow into 2L divided by N. So it's going to be 2L, L, 2L divided by 3, 2L divided by 4, which is L over 2, 2L divided by 5, okay, so on and so forth. Harmonic numbers are whole numbers. Okay? Whole numbers. You cannot have half of a harmonic. Okay? Harmonics are whole numbers. Okay? So that's how we would get the wavelength from that. To get the frequency, we would plug that into our wave speed equation. So V equals lambda times F. And we would substitute this in for wavelength and then solve for frequency from that. Okay, so you can solve for the frequency using that, but it's easier to visualize, I feel, using the wavelength. Okay? The next standing wave we look at is for an open tube. And this is a air pipe that is open on both ends. The best example of this is like a flute. So again, we have a tube that is length L. The only thing that's different about an open tube is the fact that now, instead of having nodes on each end, we must have antinodes on each end. Okay? But we're going to see a very similar pattern here. The reason for that is because antinodes occur just as often as nodes occur. Every half wave, we have a new antinode that's formed. Okay? So in this case, we have our incident wave here. We have our wave that is reflected here. Okay? And if you look at this, we're going from peak to peak. And from peak to peak is half of a wave. Okay? So again, the wavelength of this is going to be 2L. Okay? The wavelength for that first harmonic, that fundamental frequency, will be 2L. Okay? If we look at our second wave here, the second harmonic, we have our incident wave, we have our reflected wave, and if you look at this, it goes quarter, this is a quarter of a wave, this is half a wave, this is quarter of a wave. So again, there's one full wave in that tube at that time. So the wavelength there is going to be L. Okay? The next one, same idea. Incident wave. Reflected wave. Okay? So if you look at this, now we have quarter, half, half, quarter. And so again, there's going to be 1.5 waves in there. So the wave length of just one wave, which is like from here to here, is 2/3 the length of the tube. Okay, 2L over 3. And we keep going on and so forth. If we were to look at the next one, we would see that one of those waves, so from here to here is one wave, and then from there, there's another. So the length of that is going to be L over 2. And then down here, we have one wave from here to here, one wave from here to here, and then another half wave. So the wavelength there is going to be 2/5 L. Okay? So our general form for the standing wave in an open tube is again going to be 2L over N, where N is again the harmonic, and it is again whole numbers. And again, we can plug into our wave speed equation. Substitute this in for lambda, and we'll get the frequency. I'll go ahead and put it on this slide. And once we rearrange it, we get the frequency equals NV over 2L, where N is a whole number, the harmonic number. V is the wave speed, or the speed of the wave, so in air, the speed of sound. And then over 2L, where L is the length of the tube. Okay? One more of these, and then look, this one is different. It is an open-closed tube. When you have an open-closed tube, you have to have a node on the closed end. So this is the closed end. Notice that we have nodes at each of these points. An antinode on the open end. Okay? So this is a little bit different. And the reason it's different is because the pattern to go from node to antinode occurs every quarter wave, essentially. Okay, so in order for this to happen, you get a little bit different pattern. Okay, so if we look at this first part of a wave here, okay, so notice this goes from node up to antinode. Okay, that's only a quarter of a wave. Okay, so it's only a quarter wave. So in order to have a full wave of that, we would need 4 L's. Okay, so the lambda here is going to be 4L for the fundamental frequency. Okay, if we look at our next wave, okay, that right there is 3/4 of a wave. Okay. So in order to have a full wave, we would need one more segment of that, okay? So the wavelength here is 4/3 L, or 4L over 3, okay? Because you would need one more third. Because right now we have 1, 2, 3/4 of a wave, so we would need one more in order to complete that wave, okay? Down here it's a little bit easier to see, because one full wave goes from here to here, okay? And so if you look at your segment, you have 5 quarters of a wave on the last one, okay? So 5/4 of a wave. So the wavelength there is going to be 4/5 L. So hopefully you see the pattern here, that the wavelength of this one is going to be a little bit different. It's because that node to antinode pattern is not the same as an antinode to antinode pattern or a node to node pattern. So the wavelength here, the general form of this one, is that lambda equals 4L over N, where N is the harmonic number. But what are all of these harmonics?
Attention teachers, please tune in to KMTV for the pledge and quiet reflection.
They must be odd, that is correct, okay? In order for this wave to take hold. Okay, in order for an open closed tube, sometimes it will be just referred to as a closed-ended tube, the harmonic number must be odd. Okay, and again you plug in V equals lambda times F. Once we rearrange it, F equals NV over 4L, where again N must be an odd integer. Okay, all right. Last thing we'll look at V frequency. This is something you might have heard before. When you have two different waves that have very similar frequencies, like within 8 hertz. Okay, very small numbers there. They're moving in the same direction. You get these alternating constructive and destructive interference patterns. So if you look at the diagram here, you see the blue wave and the red wave are moving in the same place. Where they are totally in phase are right here and right here. When those happen, you get these large, this constructive interference that occurs. The places where they are totally out of phase are here, here, and here. When I say out of phase, I mean the crests overlap with the troughs overlap with the crests. And so when you get that, you get totally destructive interference. That's what occurs there. Okay? To get the frequency that you hear these beats, where the constructive and destructive interference occurs, you just take the absolute value of the difference between those two frequencies. Okay, so the frequency of the blue line, the frequency of the red line, subtract those two, find the absolute value, and that's how you get the beat frequency. Thanks.